Langchain Elastic Search Cache. Description: the Langchain Elastic Search Cache allows you to store and retrieve responses from your LLM models within an Elasticsearch index, enabling efficient caching and retrieval of past interactions. Inputs: query the input query or prompt provided to the LLM. LLM response: the response generated by the LLM for the given query. Outputs: cached LLM response: the previously cached response for a given query. If available. Steps: query indexing: when a new query is processed, the query and corresponding LLM response are indexed into the Elasticsearch index. Query retrieval: when a query is received, the cache checks if the query or a similar query exists in the index. Response retrieval: if a matching query is found, the associated LLM response is retrieved from the cache. Metrics: cache hit rate: the percentage of queries that result in a cache hit retrieval of a previously cached response. Cache miss rate: the percentage of queries that result in a cache miss, no matching query found in the cache. Visualization plots: cache hit rate over time: a plot visualizing the cache hit rate over a specified time period, highlighting trends in cache performance. Query distribution: a plot depicting the distribution of different queries processed by the cache, providing insights into query patterns. Fine-tune parameters: index name: the name of the Elasticsearch index used for storing the cached responses. Cache size limit: the maximum number of cached responses allowed in the index. Similarity function: the function used to determine the similarity between queries and cached queries. Influencing cache hit rates. Uncertainty methods. Query similarity score: a score representing the similarity between the current query and cached queries, providing a measure of uncertainty about the retrieved response. LLM response confidence: if the LLM provides confidence scores for its response, this can be used as an uncertainty indicator. Challenges and fixes. Challenge 1: query ambiguity: queries with similar wording but different meanings can result in incorrect cache hits. Sample use case that resulted in challenge 1: a query "What is the capital of France?" might be incorrectly matched with a cached response for "What is the currency of France?" Fixes to challenge 1: use more sophisticated similarity functions for query matching. Implement query understanding capabilities to differentiate queries with similar wording but different intentions. Challenge 2: cache size management: a large cache can consume significant memory and resources, potentially impacting performance. Sample use case that resulted in challenge 2: as more queries are cached, the cache might grow too large and become slow to query. Fixes to challenge 2: implement a cache eviction strategy to remove older or less frequently used entries. Consider using a distributed cache solution for scalability. Challenge 3: LLM response variability: LLMs can generate different responses for the same query, potentially leading to inconsistent cache results. Sample use case that resulted in challenge 3: for the same query, the LLM might generate different variations of the answer due to stochasticity or changes in its model parameters. Fixes to challenge 3: consider caching the average of multiple LLM responses for a given query to reduce variability. Employ techniques like response deduplication to ensure that similar responses are only stored once in the cache. Challenge 4: cache invalidation: changes in the underlying data or information used by the LLM might require cache invalidation. Sample use case that resulted in challenge 4: if a database used by the LLM is updated, the cached responses based on outdated information might become inaccurate. Fixes to challenge 4. Implement mechanisms for automatic cache invalidation when relevant changes are detected. Use a cache aside pattern where data is first fetched from the primary source before checking the cache. Langchain Elastic Search Cache. Elasticsearch Cache description. Explain in detail. The Elasticsearch Cache is a caching mechanism for Langchain that uses Elasticsearch as the storage backend. This is particularly useful for storing and retrieving large amounts of data that need to be accessible quickly. Inputs. Input 1. Explain in detail. This cache accepts an index name and a document ID as input to store or retrieve data. Input 2. Explain in detail. The document to be stored in the cache is also an input. This can be any Python object that can be serialized to JSON. Outputs. Output 1. Explain in detail the cached document retrieved based on the index name and document ID. Output 2. Explain in detail a Boolean value indicating if the document was successfully stored in the cache. Steps. Step 1. Explain in detail. The Elasticsearch Cache class initializes a connection to the specified Elasticsearch instance. Step 2. Explain in detail. To store a document, the cache uses the provided index name and document ID to store the serialized document in the Elasticsearch index. Step 3. Explain in detail. To retrieve a document, the cache uses the index name and document ID to query the Elasticsearch index and retrieve the corresponding document. This retrieved document is then deserialized into its original Python object. Metrics. Metric 1. Explain in detail. Cache hit rate measures the percentage of times a document is found in the cache. Metric 2. Explain in detail. Cache miss rate measures the percentage of times a document is not found in the cache. Metric 3. Explain in detail. Average latency for cache operations measures the average time taken to store or retrieve a document. Visualization plots. Visualization plot 1. Explain in detail time series plot of cache hit rate over time. Visualization plot 2. Explain in detail histogram of cache latency. Fine-tune parameters. Parameter 1. Explain in detail index name. The name of the Elasticsearch index to use for caching. Parameter 2. Explain in detail documented. The unique identifier for each document stored in the cache. Parameter 3. Explain in detail sClient. An optional parameter to specify the Elasticsearch client to be used. If not provided, the cache will create a default Elasticsearch client. Parameter 4. Explain in detail max cache size sets a limit on the maximum number of documents that can be stored in the cache. This can be used to prevent the cache from consuming too much memory. Uncertainty methods. Uncertainty method 1. Explain in detail. The Elasticsearch cache does not have built-in uncertainty methods. To estimate uncertainty, you can consider implementing a separate uncertainty estimation layer that interacts with the cache. To track and analyze document retrieval times, hit rates, and potentially include metadata related to the uncertainty of the cached data. Uncertainty method 2. Explain in detail if dealing with outdated data. Consider using timestamps and version control within the cached data to track updates and potential inconsistencies. Challenges and fixes. Challenge 1. Explain in detail challenge difficulty managing large cache sizes. Storing a large number of documents in the cache can consume significant memory and impact performance. Sample use case that resulted in challenge 1 when caching a large dataset of user profiles. The cache might grow beyond available resources, leading to slowdowns or crashes. Fixes to challenge 1. Implement the cache eviction strategy, such as least recently used LRU. To remove older or less frequently accessed documents from the cache, utilize a more efficient caching mechanism like Redis, which is designed for high-performance caching. Consider using a tiered caching approach, where frequently used documents are stored in a fast, in-memory cache while less frequently used documents are stored in a slower, disk-based cache. Challenge 2. Explain in detail challenge data inconsistency between the cache and the source of truth. If the source data changes, the cached data may become outdated. Sample use case that resulted in challenge 2. If a user updates their profile information in the source database, the cached profile may remain outdated until it is refreshed. Fixes to challenge 2. Implement a mechanism to invalidate or refresh cached data when the source data changes. This could involve using event listeners or periodic updates to ensure cache consistency. Consider using a cache aside pattern, where the cache is used as a temporary store for frequently accessed data, while the source database remains the authoritative source. Challenge 3. Explain in detail challenge the Elasticsearch cache can only be used with data that can be serialized to JSON. This means that certain complex data structures or objects may not be suitable for caching. Sample use case that resulted in challenge 3. If the application stores data in custom objects that are not JSON serializable, these objects cannot be cached using the Elasticsearch cache. Fixes to challenge 3. Use a different caching mechanism that supports other data serialization formats. Implement a custom serialization logic to convert non-JSON serializable data into a JSON format before storing it in the cache. Consider using a caching solution that is designed for more complex data types, such as a graph database or a document store. Langchain Elasticsearch Chat History. Description: the Langchain Elasticsearch Chat History module enables the preservation and retrieval of conversational context from Elasticsearch. This facilitates natural and engaging interactions, allowing for a more comprehensive understanding of the user's intent and history. Inputs. Chat history: a list of tuples, each tuple representing a message exchange, comprising the user's input and the is response. Outputs. Persisted chat history: the chat history is stored in Elasticsearch, enabling retrieval for future interactions. Steps. Data preprocessing: the chat history is prepared for storage in Elasticsearch, potentially involving cleaning and formatting. Index creation: an Elasticsearch index is created or an existing one is used to store the chat history data. Data indexing: the chat history is indexed into the Elasticsearch index, making it searchable. Metrics. Indexing time: the time taken to index the chat history data into Elasticsearch. Retrieval time: the time required to retrieve chat history from Elasticsearch. Visualization plots. Chat history timeline: a visual representation of the chat history, highlighting timestamps and message types. User message frequency: a bar chart showing the frequency of different message types user in the chat history. Fine-tune parameters. Elasticsearch index name specifies the name of the Elasticsearch index where the chat history will be stored. Mapping defines the structure and data types of the fields in the Elasticsearch index. Uncertainty methods. Confidence scores: assign confidence scores to the is responses based on the retrieved chat history context. Challenges and fixes. Challenge 1: data integrity, ensuring the consistency and accuracy of the chat history data stored in Elasticsearch. Sample use case that resulted in challenge 1: duplicate messages or missing information in the chat history. Fixes to challenge 1: implement data validation checks before indexing. Enforce uniqueness constraints. and provide mechanisms for data correction. Challenge 2: performance: maintaining efficient indexing and retrieval speeds for large chat histories. Sample use case that resulted in Challenge 2: slow response times when retrieving chat history from Elasticsearch. Fixes to Challenge 2: optimize Elasticsearch settings, such as indexing strategies and shard allocation. Consider using caching mechanisms for frequently accessed data. Challenge 3: scalability: handling increasing chat history sizes and user interactions. Sample use case that resulted in Challenge 3: performance degradation as the chat history volume grows. Fixes to Challenge 3: employ Elasticsearch scaling strategies, such as adding nodes or increasing resource allocation. Implement data retention policies to manage storage capacity. Langchain Elastic Search Chat History. Elasticsearch Chat Message History. Description: the Elasticsearch Chat Message History class is a Langchain tool that uses Elasticsearch to store and retrieve chat history. This allows for persistent conversation memory, enabling more context-aware and engaging interactions. Inputs: Elasticsearch Client, a configured Elasticsearch Client object for connecting to and interacting with the Elasticsearch index. Index name: the name of the Elasticsearch index where chat history is stored. Conversation ID: a unique identifier used to group messages belonging to the same conversation. Outputs: chat history: a list of chat messages retrieved from Elasticsearch based on the provided conversation ID. Each message is represented as a dictionary containing details like role, user agent, content, and timestamp. Chat history metadata: information about the stored chat history, such as the number of messages, last accessed time, and related metadata. Steps: initialization: the Elasticsearch Chat Message History class is initialized with the Elasticsearch Client index name and conversation ID. Message storage: when a new chat message is received, it is formatted into a dictionary with relevant details and indexed into the designated Elasticsearch index under the associated conversation ID. Message retrieval: when retrieving chat history, the class queries the Elasticsearch index using the conversation ID to fetch all messages belonging to that conversation. Metrics: index size: the size of the Elasticsearch index storing chat history can be tracked to monitor storage consumption. Message count: the number of messages stored in the index provides insights into conversation activity. Visualization plots: chat history timeline: a visualization depicting the chronological sequence of messages within a conversation. Message distribution: a chart illustrating the distribution of message types user agent over time. Fine-tune parameters: index settings: optimizing Elasticsearch index settings, e.g., shard count. Refresh interval can influence performance and storage efficiency. Message structure: the structure of the message dictionary can be customized to include additional metadata or fields. Uncertainty methods: confidence scores: the system can assign confidence scores to retrieved messages, reflecting the likelihood of their relevance to the current conversation. Contextual weighing: messages can be weighted based on their contextual relevance to the current query, allowing for more nuanced retrieval. Challenges and fixes: Challenge 1: scalability: handling large volumes of chat history can lead to performance bottlenecks. Sample use case that resulted in Challenge 1 in a high-traffic chatbot. The Elasticsearch index grew significantly, resulting in slower query responses and increased latency. Fixes to Challenge 1: sharding: divide the index into smaller shards for parallel processing and faster retrieval. Index optimization: tune Elasticsearch settings, e.g., refresh interval, number of replicas to improve performance. Data pruning implement a strategy for removing older or less relevant messages from the index to maintain manageable size. Challenge 2. Data security. Protecting sensitive information stored in chat history is critical. Sample use case that resulted in Challenge 2. A conversation contained personal data that needed to be secured against unauthorized access. Fixes to Challenge 2. Access control. Configure Elasticsearch with appropriate access controls to restrict access to sensitive data. Encryption. Encrypt chat messages before storing them in the index. Data masking. Redact or mask sensitive information within the message content before storage. Challenge 3. Message deduplication. Avoiding duplicate messages in the chat history is crucial for accurate and consistent retrieval. Sample use case that resulted in Challenge 3. A network issue caused the same message to be sent multiple times, resulting in duplicates in the chat history. Fixes to Challenge 3. Unique identifiers. Use unique message identifiers to prevent duplicates. Timestamp comparison. Compare timestamps to identify and remove duplicate messages based on their time of arrival. Message hashing. Calculate a hash of the message content to detect duplicates. Langchain Elasticsearch Client. Description. The Langchain Elasticsearch Client is a powerful tool that allows you to leverage the capabilities of Elasticsearch for your Langchain projects. It acts as a bridge between your Langchain applications and the vast data stored within your Elasticsearch indices. This client enables you to retrieve relevant documents from Elasticsearch. Use them for tasks like question answering, text summarization, and document generation, all within the Langchain framework. Inputs. Index. The name of the Elasticsearch index to search within. This is crucial for specifying the specific data source to query. Query. The search query that you want to execute against the specified Elasticsearch index. This query can be a simple keyword or a more complex structured query based on Elasticsearch's query language. Filter. Optional. Additional filter criteria to refine the search results. This can be used to narrow down the results based on specific fields or values. Size. Optional. The maximum number of documents to retrieve from Elasticsearch. This helps to control the amount of data returned and avoid overwhelming your application. Outputs. Documents. A list of documents retrieved from Elasticsearch based on your query and filter criteria. Each document is represented as a Python dictionary, making it easy to access and process the information. Steps. Query construction. Langchain constructs a search query based on the input you provide, taking into account the index, query, filter, and size parameters. Elasticsearch interaction. The client interacts with your Elasticsearch instance, sending the crafted query to retrieve relevant documents from the specified index. Data transformation. The retrieved documents are transformed into a format that is compatible with Langchain. This typically involves extracting relevant fields and converting them into a Python dictionary. Structure. Metrics. Query execution time. The time it takes for Elasticsearch to process and return the search results. Number of documents retrieved. The total number of documents retrieved from Elasticsearch based on the search criteria. Visualization. Plots. Search results distribution. A plot showing the distribution of retrieved documents across different fields or categories. Query performance analysis. A plot illustrating the time it takes to execute different queries against your Elasticsearch index, allowing for performance analysis. Fine-tune parameters. Size. This parameter directly influences the number of documents returned by Elasticsearch, allowing you to control the amount of data you want to retrieve and process. Filter. By customizing the filter criteria, You can target specific aspects of your data, leading to more precise and relevant search results. Uncertainty methods. Relevance scores. Elasticsearch provides relevance scores for each retrieved document, indicating how closely they match your search query. These scores can be used to assess the uncertainty of the search results. Document confidence. By analyzing the content of the retrieved documents, you can estimate the confidence level of the information provided, allowing for a more nuanced understanding of the results. Challenges and fixes. Challenge 1. The Elasticsearch index may not contain relevant data for the given query, resulting in empty or irrelevant results. Sample use case that resulted in Challenge 1: searching for climate change in an index containing only financial data. Fixes to Challenge 1. Ensure that the specified index contains relevant information. Refine the search query to better match the contents of the index. Challenge 2. The search query might be too broad, leading to a large number of irrelevant documents being retrieved. Sample use case that resulted in Challenge 2: searching for cars in an index containing information on all types of vehicles. Fixes to Challenge 2. Narrow down the search query by adding more specific keywords or filters. Use Elasticsearch's query language to construct more precise search queries. Challenge 3. The Elasticsearch instance might be slow or unresponsive, delaying the retrieval of search results. Sample use case that resulted in Challenge 3: searching a large and heavily loaded Elasticsearch index. Fixes to Challenge 3. Optimize your Elasticsearch cluster configuration to handle high search load. Consider using a caching layer to reduce the number of requests to Elasticsearch. Langchain Elasticsearch Client. Create Elasticsearch Client. Description: this function creates an Elasticsearch client object that can be used to interact with an Elasticsearch index. Inputs: Elasticsearch URL, the URL of the Elasticsearch server. Index name, the name of the Elasticsearch index to connect to. Outputs: Elasticsearch client, an Elasticsearch client object that can be used to interact with a specified Elasticsearch index. Steps: the function first imports the necessary libraries, including the Elasticsearch Python client. It then creates an Elasticsearch client object using the provided Elasticsearch URL and index name. Metrics: query execution time, the time it takes to execute a query against the Elasticsearch index. Number of documents retrieved, the number of documents returned by a query. Visualization plots: histogram of document frequencies. This plot shows the distribution of document frequencies in the Elasticsearch index. Scatter plot of document scores. This plot shows the relationship between document scores and other document attributes. Fine-tune parameters: index settings, parameters that control the indexing process, such as the number of shards and replicas. Query settings, parameters that control the search process, such as the query type and scoring function. Uncertainty methods: Bayesian inference. This method can be used to estimate the probability of a document being relevant to a given query. Ensemble methods: this method can be used to combine the predictions of multiple models to improve accuracy. Challenges and fixes: Challenge 1: connection errors. The Elasticsearch client may fail to connect to the server due to network issues or incorrect server configuration. Sample use case that resulted in Challenge 1: trying to connect to an Elasticsearch server that is not running or is not accessible from the current network. Fixes to Challenge 1: check that the Elasticsearch server is running and accessible from the current network. Verify the Elasticsearch URL and index name are correct. Challenge 2: authentication issues. The Elasticsearch client may fail to authenticate with the Server due to incorrect credentials or insufficient permissions. Sample use case that resulted in challenge 2 trying to connect to an Elasticsearch server that requires authentication without providing the correct credentials. Fixes to challenge 2 provide the correct credentials for the Elasticsearch server. Ensure that the user account has sufficient permissions to access the specified index. Challenge 3 indexing errors. The Elasticsearch client may fail to index documents due to errors in the document data or the Elasticsearch configuration. Sample use case that resulted in challenge 3 trying to index a document that contains invalid data or is missing required fields. Fixes to challenge 3 verify that the document data is valid and conforms to the Elasticsearch schema. Check the Elasticsearch configuration for any indexing errors. Challenge 4 query errors. The Elasticsearch client may fail to execute queries due to syntax errors or incorrect query parameters. Sample use case that resulted in challenge 4 using an invalid query syntax or specifying incorrect query parameters. Fixes to challenge 4 review the query syntax and parameters to ensure that they are correct. Use the Elasticsearch documentation to help with the query construction. Langchain Elasticsearch embeddings. Description: Langchain's Elasticsearch embeddings component leverages the power of Elasticsearch to efficiently store and retrieve text embeddings for various NLP tasks like semantic search, question answering, and document summarization. Inputs. Text: the input text to be embedded. This could be a single document, a collection of documents, or even a single sentence. Elasticsearch index: the name of the Elasticsearch index where the embeddings will be stored or retrieved from. Outputs. Embeddings: a numerical representation of the input text, capturing its semantic meaning. These embeddings are stored in Elasticsearch for efficient search and retrieval. Search results when querying the embeddings stored in Elasticsearch. The output includes the most relevant documents based on semantic similarity to the query. Steps. Text preprocessing: the input text undergoes preprocessing steps like tokenization, normalization, and stemming to prepare it for embedding generation. Embedding generation: a pre-trained embedding model like sentence transformers or OpenAI embeddings is used to convert the preprocessed text into a numerical vector representation. Elasticsearch indexing: the generated embeddings are then indexed into the specified Elasticsearch index, allowing for efficient search and retrieval. Querying and retrieval: when a query is submitted, it is also embedded using the same embedding model. Elasticsearch then performs a similarity search against the stored embeddings to identify the most relevant documents. Metrics. Embedding quality evaluated using tasks like semantic similarity, paraphrasing, and question answering to assess the ability of the embeddings to capture semantic meaning. Search performance measured by metrics like precision, recall, and F1 score, indicating the accuracy of the retrieved documents based on relevance to the query. Visualization plots. Embedding space visualization: visualizing the embedding space using dimensionality reduction. Techniques like tsna helps understand the relationships between different texts based on their embeddings. Search results visualization: plotting the retrieved documents with their relevance scores can provide insights into the search performance and identify potential biases in the results. Fine-tune parameters. Embedding model: different embedding models, e.g., sentence transformers. OpenAI embeddings can be selected based on the specific requirements of the task and the available computational resources. Elasticsearch index settings. Optimizing Elasticsearch index settings, like the number of shards and replicas, can improve search performance and scalability. Uncertainty methods. Confidence scores. Elasticsearch can provide confidence scores for the retrieved documents, indicating the likelihood of their relevance to the query. Ensemble methods. Combining multiple embedding models or multiple Elasticsearch indices can reduce uncertainty by leveraging different perspectives and improving the robustness of the results. Challenges and fixes. Challenge 1. Embedding dimensionality. High-dimensional embeddings can lead to computational challenges and performance issues. Sample use case that resulted in Challenge 1. A large-scale document collection with millions of documents might require a high-dimensional embedding model, resulting in slower search performance. Fixes to Challenge 1. Dimensionality reduction. Applying techniques like PCA or T-snake can reduce the dimensionality of the embeddings without significantly affecting the semantic information. Elasticsearch indexing optimization. Adjusting index settings like the number of shards and replicas to optimize indexing and search performance for high-dimensional data. Challenge 2. Cold start. When a new index is created, there are no existing embeddings to perform searches. Sample use case that resulted in Challenge 2. A new knowledge base is being implemented, and there are no pre-existing embeddings for the documents. Fixes to Challenge 2. Initial seed embeddings. A small initial set of embeddings can be pre-populated in the index to provide some starting point for search. Gradual indexing. Embeddings can be gradually added to the index as new documents are processed, avoiding a large initial indexing effort. Retrieval with external embeddings. If there are no existing embeddings, a separate embedding model can be used to generate embeddings for the query and perform a search against the document collection directly. Langchain Elastic Search Embeddings. Elasticsearch embeddings. Description. Explain in detail. Elasticsearch embeddings is a Langchain embedding class that utilizes Elasticsearch to store and retrieve embeddings. It leverages Elasticsearch's indexing and search capabilities to efficiently handle large-scale embedding storage and retrieval operations. Inputs. Input 1. Explain in detail text, the input text to be embedded. Input 2. Explain in detail Elasticsearch client, a connection to the Elasticsearch instance where the embeddings are stored. Input 3. Explain in detail index name, the name of the Elasticsearch index where the embeddings are stored. Input 4. Explain in detail embedding function, the function used to generate embeddings for the input text. It can be a pre-trained model like OpenAI's text embedding or DA002 or a custom embedding function. Outputs. Output 1. Explain in detail embedding, the resulting embedding vector representing the input text. The format of the embedding depends on the chosen embedding function. Steps. Step 1. Explain in detail the input text is sent to the embedding function to generate its corresponding vector representation. Step 2. Explain in detail the generated embedding is then stored in the specified Elasticsearch index. A unique identifier e.g. document ID can be associated with the embedding for retrieval purposes. Metrics. Metric 1. Explain in detail embedding quality, the performance of the embedding function in representing the semantic meaning of the input text. This can be evaluated using metrics like cosine similarity or perplexity on downstream tasks. Metric 2. Explain in detail retrieval accuracy, the ability of Elasticsearch to retrieve relevant embeddings based on similarity queries. This can be measured using recall, precision, and F1 score metrics. Visualization plots. Visualization plot 1. Explain in detail embedding visualization, visualizations of the embedding space can help understand the relationships between different embeddings. Techniques like tsna or PCA can be used for dimensionality reduction. Fine-tune parameters. Parameter 1. Explain in detail index configuration. The settings for the Elasticsearch index can be optimized for embedding storage and retrieval. This includes parameters like shard count, replica count, and similarity scoring functions. Uncertainty methods. Uncertainty method 1. Explain in detail embedding uncertainty estimation. It's possible to estimate the uncertainty associated with the generated embedding. This can be achieved by techniques like dropout or ensemble methods. Challenges and fixes. Challenge 1. Explain in detail large-scale embedding storage. Handling a massive number of embeddings in Elasticsearch can be challenging. Sample use case that resulted in Challenge 1. Processing the corpus with millions of documents, resulting in a large number of embeddings. Fixes to Challenge 1. Optimizing the Elasticsearch index configuration for efficient storage and retrieval. Leveraging sharding and replication strategies. And exploring techniques like data compression. Challenge 2. Explain in detail search performance. Retrieving the most relevant embeddings from Elasticsearch can be computationally intensive for large datasets. Sample use case that resulted in Challenge 2. Performing semantic search on a large corpus of text, resulting in slow query times. Fixes to Challenge 2. Optimizing the Elasticsearch query parameters, using appropriate scoring functions, and exploring approximate search techniques for faster retrieval. Challenge 3. Explain in detail memory usage. Loading embeddings into memory for processing can be memory intensive, especially for large datasets. Sample use case that resulted in Challenge 3. Applying machine learning models on a dataset with high-dimensional embeddings. Fixes to Challenge 3. Exploring techniques like embedding quantization to reduce memory footprint, using lazy loading strategies to load embeddings on demand, and leveraging distributed computing frameworks for parallel processing. Challenge 4. Explain in detail cold start problem. When a new embedding is added to the index, it may not be readily accessible for similarity search until it's indexed by Elasticsearch. Sample use case that resulted in Challenge 4. Adding new embeddings during runtime and querying for their similarities immediately. Fixes to Challenge 4. Implementing strategies like pre-warming the index or using a separate cache for recently added embeddings. Langchain Elastic Search Embeddings Embedding Service Adapter. Description. Explain in detail the embedding service adapter allows you to use Elasticsearch as an embedding store, making it possible to perform vector similarity search directly on the embedded data within Elasticsearch. This is a powerful technique for building applications like semantic search, question answering, and recommendation systems. Inputs. Input 1. Explain in detail. This is the text data that you want to embed. It can be a single string or a list of strings. Input 2. Explain in detail. The embedding service adapter requires an instance of an embedding model, like OpenAI embeddings or Hugging Face embeddings, to convert the text data into numerical embeddings. Outputs. Output 1. Explain in detail. The embedding service adapter returns the generated embeddings, which are numerical representations of the input text data. Output 2. Explain in detail. If you use the add documents method, the embedding service adapter also saves the embedded data to Elasticsearch for later retrieval and similarity search. Steps. Step 1. Explain in detail. The embedding service adapter first calls the specified embedding model to convert the input text into numerical embeddings. Step 2. Explain in detail. Next, the adapter sends the generated embeddings to Elasticsearch for storage. Metrics. Metric 1. Explain in detail. You can use various metrics to evaluate the performance of pay. Embedding model, such as mean average precision map or recall K. These metrics are typically calculated after performing a similarity search. Metric 2. Explain in detail. You can also monitor the performance of Elasticsearch itself. Looking at metrics like indexing speed, search latency, and resource utilization. Visualization plots. Visualization plot 1. Explain in detail. Visualization plots can be used to assess the quality of pay. Embeddings. For example, you can create scatter plots to see how the embeddings are distributed in vector space. Or use tsna to visualize high-dimensional embeddings in a lower-dimensional space. Visualization plot 2. Explain in detail. Visualization can also be helpful for understanding pay results of a similarity search, such as plotting the top-ranked documents for a given query. Fine-tune parameters. Parameter 1. Explain in detail. The embedding service adapter inherits parameters from the underlying embedding model, such as the model name for Hugging Face models or a PI key for OpenAI models. Parameter 2. Explain in detail. You can also customize Elasticsearch specific parameters, such as the index name for the index where you will store the embeddings. Uncertainty methods. Uncertainty method 1. Explain in detail. You can use Bayesian methods to estimate the uncertainty of embeddings generated from probabilistic embedding models. This can help you understand the reliability of the embeddings and potentially refine pay similarity search process. Uncertainty method 2. Explain in detail. Ensemble methods, which combine multiple embedding models, can also be used to assess the uncertainty of the embeddings. Challenges and fixes. Challenge 1. Explain in detail. Handling large datasets. Embedding large volumes of data can be computationally expensive and resource-intensive. Sample use case that resulted in challenge 1. You might encounter performance issues when embedding and storing millions of documents in Elasticsearch. Fixes to challenge 1. Consider using techniques like chunking or batching to process large datasets efficiently. You can also explore optimizing the Elasticsearch configuration to handle the increased load. Challenge 2. Explain in detail. Maintaining high search accuracy. Ensuring that the embeddings accurately represent the semantic meaning of the text is crucial for successful similarity search. Sample use case that resulted in challenge 2. You may find that the similarity search results are not always relevant, meaning that the embeddings are not capturing the nuances of the text adequately. Fixes to challenge 2. Experiment with different embedding models and fine-tune their hyperparameters to improve their accuracy. You can also explore data augmentation techniques to enrich the training data and improve pay quality of the embeddings. Langchain Elasticsearch retrievers. Description. Langchain Elasticsearch retrievers enable retrieving relevant documents from an Elasticsearch index based on a user query. They leverage Langchain's modularity, allowing integration with other components like LLMs for question answering or summarization. Inputs. Query the user's question or text prompt that triggers the search. Elasticsearch index. The specific Elasticsearch index where the relevant documents reside. Elasticsearch client. A connection object to communicate with the Elasticsearch instance. Outputs. Retrieved documents. A list of relevant documents fetched from the Elasticsearch index based on the query. Document embeddings. Optional embeddings of the retrieved documents that capture their semantic meaning, allowing for further analysis and comparison. Steps. Query processing. The user's query is preprocessed to remove noise and improve its search relevance. E.g., stemming, stop word removal, Elasticsearch query generation. The processed query is translated into an Elasticsearch query format, leveraging specific query syntax and techniques, e.g., keyword matching, Boolean operators, fuzzy search, document retrieval. The generated Elasticsearch query is executed on the specified index. Retrieving matching documents. Document scoring. The retrieved documents are scored based on their relevance to the query. Potentially utilizing Elasticsearch's ranking algorithms, e.g., TF-IDF, BM25. Result filtering. The top scoring documents are selected, potentially filtering by number of results or score threshold. Metrics. Retrieval accuracy measures how effectively the retriever finds relevant documents for a given query. Retrieval efficiency evaluates the speed and resource usage of the retrieval process. Visualization plots. Retrieval precision. Recall curve depicts the trade-off between precision correctly retrieved documents and recall proportion of relevant documents retrieved. Document ranking distribution visualizes the score distribution of retrieved documents, highlighting the top-ranked results. Fine-tune parameters. Elasticsearch query parameters. Various parameters controlling the Elasticsearch search behavior, such as query fields, boosting factors, and scoring algorithms. Retrieval threshold. The minimum score or number of results required to be considered relevant. Uncertainty methods. Confidence scores assign scores to retrieved documents, indicating the retriever's certainty about their relevance. Diversity ranking. Encourage retrieving diverse documents even if they have lower scores. Challenges and fixes. Challenge 1. Inefficient search. Retrieving irrelevant documents due to poorly constructed queries or improper indexing. Sample use case that resulted in challenge 1. A query for Apple retrieves documents about fruit, not the technology company. Fixes to challenge 1. Optimize Elasticsearch query. Use more specific terms, Boolean operators, and fuzzy search options. Improve indexing. Ensure proper indexing of relevant keywords and semantic information. Challenge 2. Query ambiguity. The query might be interpreted in multiple ways, leading to inconsistent retrieval results. Sample use case that resulted in challenge 2. A query for Jaguar could refer to the animal or the car brand. Fixes to challenge 2. Contextualization. Utilize external knowledge or previous interactions to understand the user's intent. Query expansion. Use synonyms and related terms to broaden the search scope. Challenge 3. Data bias. The retriever might favor specific document types or topics due to biases in the dataset. Sample use case that resulted in challenge 3. A retriever trained on news articles might prioritize political topics over scientific articles. Fixes to challenge 3. Balanced dataset. Use a diverse dataset representing multiple perspectives and topics. Fairness algorithms. Implement fairness-aware ranking algorithms to mitigate bias. Langchain Elasticsearch retrievers. Elasticsearch retriever. Description. The Elasticsearch retriever is a Langchain retriever that uses Elasticsearch as a backend for document retrieval. It leverages Elasticsearch's powerful indexing and search capabilities to efficiently retrieve documents that are relevant to a given query. Inputs. Query. A string representing the user's query or question. This is the primary input to the retriever, and it triggers the Elasticsearch search process. Elasticsearch client. An Elasticsearch client object that provides access to the Elasticsearch server and its indices. This object is used to execute search queries and retrieve results. Outputs. Documents. A list of retrieved documents that match the query based on the Elasticsearch search results. Each document is a dictionary containing the document's content and metadata. Steps. Initialization: the Elasticsearch Retriever is initialized with an Elasticsearch client and optional configuration parameters. Query processing: the user's query is preprocessed and transformed into a format suitable for Elasticsearch search. This may involve tokenization, stemming, and other text processing techniques. Elasticsearch search: the preprocessed query is executed as a search query against the configured Elasticsearch index. Result retrieval: the Elasticsearch search results are retrieved and converted into a list of documents. Each document contains the document's content, metadata, and relevance score assigned by Elasticsearch. Metrics. Search time: this metric measures the time taken by Elasticsearch to execute the search query and return results. Number of results: this metric tracks the total number of documents retrieved by Elasticsearch. Visualization plots. Relevance score distribution: this plot visualizes the distribution of relevance scores assigned to retrieved documents by Elasticsearch. Fine-tune parameters. Index name: the name of the Elasticsearch index to search. Embedding field: the name of the field in the Elasticsearch index that stores the document. Embeddings. Search type: the type of Elasticsearch search to perform, e.g., query string, match, fuzzy. Size: the maximum number of documents to retrieve. Uncertainty methods. Confidence score: the relevance scores returned by Elasticsearch can be used as a proxy for confidence in the retrieved documents. Challenges and fixes. Challenge 1: low quality or irrelevant search results. Sample use case: a query that is too broad or ambiguous, leading to a large number of irrelevant documents being retrieved. Fixes to challenge 1. Refine the query by adding more specific keywords or phrases. Use more precise search operators in the query, e.g., phrase, boolean, wildcard. Ensure that the Elasticsearch index is properly indexed with relevant terms and keywords. Challenge 2: high search latency. Sample use case: a large and complex Elasticsearch index, leading to slow search times. Fixes to challenge 2. Optimize the Elasticsearch index for faster search performance, e.g., use appropriate indexing strategies. Optimize field mappings. Consider using Elasticsearch caching mechanisms to reduce search latency. Use a smaller index that is relevant to the specific query. Challenge 3: difficulty in retrieving documents with specific metadata. Sample use case: a query that requires retrieving documents based on specific metadata fields. But the Elasticsearch index does not have the appropriate metadata fields. Fixes to challenge 3. Add the necessary metadata fields to the Elasticsearch index. Use the filter parameter in the Elasticsearch query to retrieve documents based on specific metadata values. Challenge 4: difficulty in handling complex search queries. Sample use case: a query that requires advanced search logic, such as Boolean operators or proximity searches. Fixes to challenge 4. Use Elasticsearch's advanced query syntax to construct complex search queries. Utilize Elasticsearch's query DSL domain-specific language for more complex search scenarios. Challenge 5: handling large document sizes. Sample use case: retrieving documents that are very large in size, leading to performance issues. Fixes to challenge 5. Utilize Elasticsearch's document size limits to manage large documents efficiently. Consider using a different storage mechanism for large documents, such as an external file system. Challenge 6: handling document duplication. Sample use case: retrieving multiple copies of the same document due to indexing issues. Fixes to challenge 6. Ensure that Elasticsearch is properly configured to handle duplicate documents. Use Elasticsearch's document ID to uniquely identify each document. Challenge 7. Handling document updates and deletions. Sample use case document updates or deletions in the Elasticsearch index are not reflected in pay. Retrievers results. Fixes to challenge 7. Use Elasticsearch's update and delete APIs to maintain the consistency of the index. Implement a mechanism to refresh the retriever's cache after document updates or deletions. Langchain Elastic Search Vector Stores Approx Retrieval Strategy. Description: the approx retrieval strategy in Langchain's Elasticsearch Vector Store allows for approximate nearest neighbor search, a technique used for finding the closest vectors to a given query vector even when dealing with massive datasets. This strategy is particularly useful for large-scale applications where exact nearest neighbor search would be computationally expensive or impractical. Inputs. Query vector: the input vector for which we want to find the closest neighbors in the vector store. Vector store: the Elasticsearch index containing the embeddings of the documents. Outputs. Retrieval scores: a list of document IDs with their associated similarity scores, indicating how closely each document's embedding matches the query vector. Retrieved documents: the actual documents corresponding to the retrieved document IDs. Steps. Encoding: the query vector is encoded using the same embedding model used to create the embeddings in the vector store. Approximate nearest neighbor search: Elasticsearch's approximate nearest neighbor search algorithms, e.g., HNSW, are used to retrieve a set of candidate vectors that are likely to be closest to the query vector. Similarity calculation: the similarity between the query vector and each candidate vector is computed using the chosen similarity metric, e.g., cosine similarity. Ranking and retrieval: the candidate vectors are ranked based on their similarity scores, and the top scoring documents are retrieved from the vector store. Metrics. Recall measures the percentage of relevant documents that were retrieved from the vector store. Precision measures the percentage of retrieved documents that are actually relevant. Average precision: a more nuanced metric that combines precision and recall, taking into account the order in which relevant documents are retrieved. Visualization plots. Similarity score distribution: a histogram showing the distribution of similarity scores for retrieved documents. Retrieval performance precision recall: a plot showing the trade-off between precision and recall at different retrieval thresholds. Fine-tune parameters. K, the number of candidate vectors to retrieve during approximate nearest neighbor search. Higher K values may improve recall but increase search time. Similarity metric: the distance metric used to measure similarity between vectors, e.g., cosine similarity, Euclidean distance. Uncertainty methods. Confidence score: the similarity score between the query vector and retrieved documents can be used as an indicator of confidence in the retrieved results. Ensemble retrieval: using multiple retrieval strategies and combining their results can provide more robust and diverse results. Challenges and fixes. Challenge 1: low recall in cases where the vector space is highly dense or the embeddings are not perfectly representative of the data. The approximate nearest neighbor search may miss some relevant documents. Sample use case that resulted in challenge 1: a user searches for a document about artificial intelligence, but the vector store only retrieves documents that focus on machine learning, even though artificial intelligence is a broader concept. Fixes to challenge 1. Increase K. Increase the number of candidate vectors retrieved during approximate nearest neighbor search. Fine-tune embeddings. Experiment with different embedding models or parameters to improve K quality of the embeddings. Use a more robust similarity metric. Consider using a metric that is more resistant to noise or variations in the embedding space. Challenge 2: high search latency with large-scale datasets and complex approximate nearest neighbor search algorithms. Retrieval times can become significant. Sample use case that resulted in Challenge 2: in application that requires near instantaneous retrieval of documents experiences significant delays due to the time it takes to perform approximate nearest neighbor search. Fixes to Challenge 2: optimize Elasticsearch indexing. Configure Elasticsearch for efficient indexing and search performance, e.g., use appropriate indexing strategies, optimize shard allocation, and tune query parameters. Reduce k. Lower the number of candidate vectors retrieved during approximate nearest neighbor search to reduce search time. Utilize caching. Implement caching mechanisms to store frequently accessed results and reduce repeated searches. Challenge 3: limited scalability. As the dataset size grows, maintaining search performance can become a challenge, particularly with complex approximate nearest neighbor algorithms. Sample use case that resulted in Challenge 3: a rapidly growing knowledge base with millions of documents experiences performance degradation as the dataset size increases. Fixes to Challenge 3: optimize Elasticsearch cluster. Scale up the Elasticsearch cluster to accommodate the growing dataset size. Utilize sharding. Partition the data into multiple shards to distribute the workload across multiple nodes. Consider distributed search. Use a distributed search engine specifically designed for large-scale data and high performance. Langchain Elastic Search Vector Stores BM25 Retrieval Strategy. Description: the BM25 retrieval strategy uses the BM25 Best Match 25 ranking algorithm to retrieve documents from an Elasticsearch index based on a query. This strategy is particularly effective when working with text-heavy data and focuses on finding documents that are most relevant to the query based on term frequency and inverse document frequency. Inputs: query: the text query that is being used to search for relevant documents. This is the input that triggers the retrieval process. Elasticsearch index: the Elasticsearch index containing the documents to be searched. This is the source of data for the retrieval process. Outputs: ranked documents: a list of documents from the Elasticsearch index ranked by their relevance to the query, based on the BM25 scoring algorithm. This output provides a ranked list of potential matches for the given query. Scores: the BM25 scores associated with each retrieved document, indicating their relevance to the query. This output provides a numerical measure of the relevance of each document. Steps: query processing: the input query is processed and transformed into a format suitable for Elasticsearch search. This step involves tokenization, stemming, and other pre-processing steps to ensure accurate matching. Elasticsearch query execution: the processed query is executed against the specified Elasticsearch index. This step leverages Elasticsearch's efficient search capabilities to retrieve potentially relevant documents. BM25 scoring: the retrieved documents are then ranked using the BM25 algorithm, which calculates a relevance score based on the frequency of query terms in the document, the inverse document frequency of those terms, and document length normalization. This step ensures that documents most relevant to the query are prioritized. Metrics: mean average precision map: this metric measures the average precision across all retrieved documents for a given query. It indicates the overall quality of the retrieved results. Recall measures the proportion of relevant documents that are retrieved. This metric helps assess how well the retrieval strategy captures all relevant documents. Precision measures the proportion of retrieved documents that are actually relevant. This metric assesses the accuracy of the retrieved results. Visualization plots. Precision recall curve, a plot that visualizes the trade-off between precision and recall at different retrieval thresholds. This plot helps evaluate the effectiveness of the retrieval strategy. Cumulative gain chart, a visualization that shows the cumulative gain of retrieving documents, indicating the incremental value of retrieving more documents. Fine-tune parameters. K1 controls the impact of term frequency in the BM25 score. Higher values give more weight to terms that appear frequently in the document. B controls the impact of document length on the BM25 score. Higher values penalize longer documents. Uncertainty methods. Confidence scores. The BM25 score itself can be used as a measure of confidence in the retrieved document. Higher scores indicate greater confidence in the relevance of a document. Challenges and fixes. Challenge 1. Overly broad queries may retrieve too many irrelevant documents. Sample use case that resulted in challenge 1. Searching for apple may retrieve documents about fruit, technology, or even a person named Apple. Fixes to challenge 1. Use more specific queries with multiple keywords or phrases. Utilize Elasticsearch's query filters to narrow down the search space. Implement a threshold for the BM25 score. Only retrieving documents with scores above a certain level. Challenge 2. The BM25 algorithm may not be effective for all types of data, especially for data with complex relationships or structured information. Sample use case that resulted in challenge 2. Retrieving documents from a knowledge graph or a database with many interconnected concepts. Fixes to challenge 2. Consider using other retrieval strategies such as semantic search or graph-based retrieval that are better suited for complex data structures. Explore hybrid approaches that combine BM25 with other strategies to leverage the strengths of each approach. Fine-tune the BM25 parameters to improve performance for specific data types. Challenge 3. Elasticsearch's indexing and search performance can be impacted by large datasets, potentially leading to slower retrieval times. Sample use case that resulted in challenge 3. Working with a very large corpus of documents or a high query volume. Fixes to challenge 3. Optimize Elasticsearch's index settings for performance, such as choosing appropriate shard and replica configurations. Implement caching mechanisms to reduce the time required to retrieve documents from the index. Consider using specialized hardware or cloud-based services designed for high-volume search operations. Challenge 4. The BM25 algorithm may not effectively handle queries with complex linguistic structures or diverse vocabulary. Sample use case that resulted in challenge 4. Searching for documents with idiomatic expressions or domain-specific jargon. Fixes to challenge 4. Pre-process the documents and queries to incorporate knowledge of linguistic structures and semantic relationships. Leverage tools such as word embeddings or language models to capture the semantic meaning of words and phrases. Experiment with different BM25 parameter values to account for the complexity of the query. Language. Langchain Elastic Search Vector Stores Base Retrieval Strategy. Description: the base retrieval strategy class is the foundation for retrieval strategies used within Langchain's Elasticsearch integration. It provides a core structure for defining how documents are retrieved from an Elasticsearch index based on a query. This class serves as a base for implementing specific retrieval strategies that cater to different needs and use cases. Inputs. Query the user's input or question that the retrieval strategy aims to answer. It represents the information need being expressed by the user. Index name: the name of the Elasticsearch index containing the documents from which relevant information needs to be retrieved. Outputs: retrieved documents: a list of documents text chunks retrieved from the Elasticsearch index based on the query and the specified retrieval strategy. Steps: query processing: the retrieval strategy receives the user's query and may perform pre-processing steps to transform it into a form suitable for Elasticsearch search. This could involve tokenization, stemming, stop word removal, or other query transformations. Search execution: the retrieval strategy uses the processed query to interact with the Elasticsearch index. It executes a search request based on the defined strategy, using Elasticsearch's powerful search capabilities. Result filtering: after retrieving potential documents from Elasticsearch, the retrieval strategy may apply additional filtering criteria based on the retrieval strategies. Logic: this could involve ranking documents based on relevance scores, applying document similarity measures, or using other heuristics to refine the retrieval results. Metrics: retrieval accuracy: the percentage of retrieved documents that are actually relevant to the users query. Retrieval latency: the time taken for the retrieval strategy to return the results. Retrieval coverage: the percentage of documents in the Elasticsearch index that are considered relevant by the retrieval strategy. Visualization plots: retrieval accuracy over time: a plot showing the evolution of retrieval accuracy over different time periods. This can be used to track the performance of the retrieval strategy and identify potential issues. Retrieval latency distribution: a histogram showing the distribution of retrieval latencies. This helps understand the typical retrieval speed and identify any outliers or potential performance bottlenecks. Fine-tune parameters. K: the number of top documents to retrieve from the Elasticsearch index. Similarity function: the similarity function used to measure the similarity between the query and the documents in the index. This could be cosine similarity, Euclidean distance, or other appropriate metrics. Uncertainty methods. Confidence scores: assign confidence scores to retrieved documents based on their relevance scores and other factors. Diversity measures: utilize diversity measures to ensure that the retrieved documents cover different aspects of the user's query. Challenges and fixes. Challenge 1: retrieval strategy may return irrelevant documents. This can occur if the query is not well defined or if the document embeddings in the Elasticsearch index are not of high quality. Sample use case that resulted in challenge 1: a user asks what is the capital of France, but the retrieval strategy returns documents about the French language. Fixes to challenge 1: improve the quality of document embeddings. Enhance the query processing stage to capture more precise search intents. Implement more sophisticated retrieval strategies that take into account semantic relationships between words and concepts. Challenge 2: retrieval strategy may be slow or inefficient. This can happen if the Elasticsearch index is large or if the retrieval strategy is computationally expensive. Sample use case that resulted in challenge 2: a user submits a complex query involving multiple search terms and the retrieval strategy takes a long time to return results. Fixes to challenge 2: optimize the Elasticsearch index for faster search operations. Explore alternative retrieval strategies that are more efficient in handling large datasets. Use caching mechanisms to avoid redundant search operations. Challenge 3: retrieval strategy may not cover all relevant documents. This can occur if the document embeddings are not representative enough or if the retrieval strategy is not sufficiently comprehensive. Sample use case that resulted in challenge 3. A user asks what are the symptoms of the flu. But the retrieval strategy misses some relevant documents in the index. Fixes to challenge 3. Experiment with different embedding models and fine-tuning techniques to improve the quality of document representations. Consider using multiple retrieval strategies in combination to increase coverage. Explore techniques for retrieving documents based on semantic relationships or contextual information. Langchain Elastic Search Vector Stores Elasticsearch Store. Description: the Elasticsearch Store class in Langchain is a vector database that leverages Elasticsearch for storing and retrieving vector embeddings. It allows you to efficiently search for similar documents based on their semantic meaning. Inputs. Documents: a list of text documents that you want to store in the vector database. These documents can be in various formats, like strings, dictionaries, or objects. Embedding function: a function that takes a text document as input and returns a vector representation embedding of that document. This function is crucial for understanding the semantic meaning of your documents. You can use pre-trained embedding models like sentence transformers or OpenAI's embedding API. Outputs. Vector database: a collection of vector embeddings stored in your Elasticsearch index, allowing for fast and efficient similarity searches. Search results: when you query the vector database with a text prompt, it returns a list of documents ranked by their similarity to the query. Steps. Embedding generation: each document from your input list is passed through the specified embedding function, generating a vector representation. Indexing: the generated embeddings, along with associated metadata like document text and IDs, are indexed in your Elasticsearch database. Search: when you search with a new text query, the query is also embedded using the same embedding function. Similarity search: the embedded query is then used to search for similar vectors in your Elasticsearch index. Elasticsearch's efficient search capabilities return the most relevant documents ranked by their similarity score. Metrics. Precision: the proportion of retrieved documents that are actually relevant to the query. Recall: the proportion of relevant documents that are retrieved by the search. Mean average precision map: a measure that considers both precision and recall across different query ranks. Visualization plots. Embedding visualization: visualizing the vector embeddings in a low-dimensional space using techniques like tsna or PCA can help understand the relationships between documents. Search result ranking: plotting the retrieved document similarity scores against their ranking can help assess the performance of the vector database. Fine-tune parameters. Index name: the name of the Elasticsearch index to use for storing embeddings. Embedding field: the name of the field in the index that will store the vector embeddings. Similarity metric: the similarity metric used for comparing vectors, e.g., cosine or L2. K: the number of top similar documents to retrieve in a search. Uncertainty methods. Bayesian inference: you can use Bayesian methods to estimate the uncertainty in the similarity scores and provide confidence intervals for the retrieved documents. Ensemble methods: combining multiple embedding models or search strategies can help reduce uncertainty and improve search accuracy. Challenges and fixes. Challenge 1: inconsistent embeddings. Using different embedding functions for indexing and searching can lead to inconsistent results. Sample use case that resulted in challenge 1: you initially used a sentence transformer model for generating embeddings but later switched to OpenAI's embedding API without updating the index. Fixes to challenge 1: ensure that you use the same embedding function for indexing and searching to maintain consistency. Challenge 2. Poor performance. The performance of Elasticsearch searches can be affected by the size of the index, the dimensionality of the embeddings, and the chosen similarity metric. Sample use case that resulted in challenge 2. Your index contains a large number of documents with high dimensional embeddings, resulting in slow search times. Fixes to challenge 2. Optimize Elasticsearch settings, adjust indexing parameters, use appropriate data types, and consider using dedicated hardware for Elasticsearch. Dimensionality reduction. Apply dimensionality reduction techniques like PCA to reduce the dimensionality of your embeddings while preserving semantic relationships. Choose an efficient similarity metric. Experiment with different similarity metrics like cosine or Euclidean distance to find the best one for your use case. Langchain Elasticsearch vector stores exact retrieval strategy. Description: the exact retrieval strategy is used for retrieving documents from an Elasticsearch vector store based on an exact match of the query. This strategy is useful for scenarios where you need to find documents that match a specific query exactly, rather than finding documents that are similar to the query. Inputs: query the query string that you want to search for. This should be an exact match for the document content. Vector store: an instance of the Elasticsearch vector store class that you want to search. Outputs: documents: a list of documents that match the query exactly. Steps: the query is sent to the Elasticsearch index. Elasticsearch performs an exact match search for documents that contain the query string. The matching documents are returned as a list. Metrics: precision: the percentage of retrieved documents that are relevant to the query. Recall: the percentage of relevant documents that are retrieved. Visualization plots: precision recall curve. This plot shows the trade-off between precision and recall for different query thresholds. Fine-tune parameters: none. Uncertainty methods: none. Challenges and fixes. Challenge 1: the query may not be an exact match for any document in the index. Sample use case that resulted in challenge 1: a query "What is the capital of France?" may not be an exact match for any document in the index, even if it contains the answer Paris. Fixes to challenge 1: use a different retrieval strategy, such as the similarity retrieval strategy, which allows for approximate matches. Challenge 2: the query may be too specific, resulting in no matching documents. Sample use case that resulted in challenge 2: a query "What is the population of Tokyo?" may be too specific and may not match any document in the index. Fixes to challenge 2: use a more general query, such as "What is the population of Japan's capital?" or use a different retrieval strategy, such as the similarity retrieval strategy. Challenge 3: the index may not be well optimized for exact match searches. Sample use case that resulted in challenge 3: if the index is not properly indexed for exact matches, the search may be slow or may not return the correct results. Fixes to challenge 3: optimize the index for exact match searches by using appropriate index settings and analyzers. Langchain Elasticsearch vector stores sparse retrieval strategy. Description: the sparse retrieval strategy in Langchain's Elasticsearch vector store allows you to perform efficient sparse retrieval, which is crucial when dealing with large datasets and complex queries. It leverages the power of Elasticsearch's sparse vector search capabilities, making it ideal for tasks like semantic search, question answering, and document retrieval. Inputs: query the text query that you want to search against the vector store. This query can be a simple phrase or a more complex question. Elasticsearch Client, an instance of the Elasticsearch client that you use to interact with your Elasticsearch index containing the vector data. Index name, the name of the Elasticsearch index where your vector data is stored. Outputs. Retrieval results, a list of documents that are most relevant to the given query, ranked based on their similarity to the query's vector representation. Steps. Query encoding. The query is first transformed into a vector representation using a suitable embedding model. This representation captures the semantic meaning of the query. Vector search. The query vector is then used to search against the vector data stored in Elasticsearch. Elasticsearch's sparse vector search functionality efficiently identifies documents that are most similar to the query vector. Retrieval. The identified documents are retrieved from Elasticsearch and returned as results. Metrics. Retrieval accuracy evaluates how accurately the strategy identifies relevant documents for a given query. Retrieval efficiency measures the speed at which documents are retrieved. Visualization plots. Retrieval distribution. A visualization that shows the distribution of retrieved documents based on their similarity scores to the query. Fine-tune parameters. Search parameters. Elasticsearch offers several parameters that can be fine-tuned to control the behavior of the sparse vector search, such as k-min score, and boost. These parameters influence the number of results returned and the ranking of those results. Uncertainty methods. Confidence scores. The retrieval strategy can return confidence scores for each retrieved document, indicating how certain the model is about the relevance of the document. Challenges and fixes. Challenge 1. Insufficiently expressive embeddings. If the embedding model used to represent the query and documents is not sufficiently expressive, the retrieval strategy might not be able to accurately capture the nuances of the query and find relevant documents. Sample use case that resulted in challenge 1. A query about artificial intelligence might not retrieve documents containing the term machine learning because the embeddings do not capture the close relationship between these concepts. Fixes to challenge 1. Use a more expressive embedding model, such as a larger language model (LLM) or a model specifically trained on the relevant domain. Challenge 2. Indexing efficiency. Building and maintaining a large vector index can be computationally expensive, particularly for large datasets. Sample use case that resulted in challenge 2. Indexing millions of documents can take significant time and resources. Fixes to challenge 2. Utilize Elasticsearch's indexing optimization techniques, such as bulk indexing and sharding, to improve indexing efficiency. Consider using techniques like approximate nearest neighbor search and to reduce the computational complexity of the search operation.